stream can also, at the end of the day, it will go out somehow after passing through this quantum region. Well, and also one should reconsider the Hawking radiation, given that there is no absolute horizon. So this is what I wanted to say. Oh, I should add the names. So this paradigm was formulated by Ashtekar and Martin Boyovald several years ago, when Ashtekar, Pawłowski, and Singh discovered the big bounce of cosmological models of homogeneous spacetimes. But recently, during the last 2 years, it was some specific model was formulated by Carlo Rovelli, in which he's even trying to calculate the time of explosion of black hole. But as I say, it's qualitative, so we shouldn't trust it.
Okay, thank you. We have limited amount of time. Do either of you want to respond to that?
I have a remark concerning this topic of putting symmetries first. I mean, we aren't sure that Einstein ever interpreted his special relativity in the sense which you offered, that putting symmetries first and then deriving Maxwell's equations. I think this came only by the work of Eugene Wigner 30 years later or so in his program. So only from that work we know how this program works, starting with a symmetry group and deriving the field equations. This is my first point. And the other point, as far as I know, this doesn't work for general relativity, because the topic of having irreducible representations of the differential group is much harder than for ordinary Lie groups. So in this case, we cannot really claim that the GR field equations do fall from symmetries.
Well, I've read Einstein's paper, Special Relativity, many times. It's so beautiful. It's true that the modern way of stating it, as you did, rely on Wigner and many others. That's how we would teach it today. But there's no question that that's how the genesis of that modern point of view comes from Einstein's paper. He starts out with a few postulates which refer not to electromagnetism, except this no direction of the speed of light, and from those and derives, well, let's put it this way. After he discusses the symmetries of space-time from that postulate, he and others then realized that all of physics has to be made consistent with Einstein's equation, with Lorentz or symmetry. And of course, having derived it in a sense, the starting point was electromagnetism. He didn't have to rederive Maxwell's equations. But he and Planck and many others immediately provided the consistent, relativistically and very informal all of other classical physics.
And I think one can say that the move here is really putting the kinematics or the transformation properties of the kinematical quantities first, and not looking for the symmetry properties or the transformation properties within the dynamics. And then, of course, as I pointed out, it's another step then to say that the symmetry comes even before the kinematics, in the sense of the kinematical quantities you have, and by giving you this whole space of possibilities.
There is another fascinating aspect of all this, which I didn't have time to discuss, and which is global symmetry versus local symmetry, which Wigner helped us understand. We're still struggling with, because although symmetry, global symmetries of nature, like Lorentz invariants, are actually physical transformations of the laboratory. You do something, you get a new situation, you get the same results. The laws of physics are invariant. Gauge symmetries are symmetries of our description of it, they're redundancies. And so even the word symmetry is perhaps a little misguided. And we're still struggling with what that means. And by the way, the modern view we now have of dualities say string theory, which has no gauge degrees of freedom, and gauge theory, which has no spatial degrees of freedom, no space at all, is a duality between two redundant or locally gauge invariant. One is diffeomorphism invariance and the other is Yang-Mills gauge invariance. Two redundant descriptions of the same thing. And that deep understanding of local symmetries, which after all we now think of as the fundamental symmetries of nature, not global symmetries which are properties truly not of the properties of the underlying physical framework, but rather of the state we live in. We're still struggling to truly understand.
Brief comments, please.
A remark on the symmetry. Einstein expressed this principle of symmetry first, and laws as a result of that very clearly, explicitly, years later in his meaning of relativity. And there he begins with classical physics. There he gives a tensor formulation of classical physics, and even there, for the first time, he shows that symmetry first, laws later, so I agree with your assessment. And another brief remark, David, at the beginning, posed a question or made a remark if everybody accepted the equivalence principle. Now, there were serious attempts to accommodate gravity within special relativity. To do that, you have to give up the equivalence principle. There were physicists who were willing to pay the price. All of Einstein's work in Prague, six papers on relativity were motivated by Max Abraham's attempts to do that and his criticism of that work.
I wanted to ask about a somewhat different question. You said you learned relativity from Weinberg's book. And
No. I actually learned relativity from Weinberg.
Oh.
I took the only graduate course I took on general relativity, which, believe me, at that time, for somebody who was interested in particle physics, was kind of, something we did on the side.
That's a bit peripheral to my question, because I believe that book never talks about black holes at all. And so I wanted to ask the two of you to perhaps comment a little bit about this. I mean, the Schwarzschild solution came immediately after the field equations. And of course, it's complicated because in the way that it was written down by Schwarzschild, there's a coordinate singularity at r equals 2m, which we know now is unimportant, but confused matters. And then there's another real singularity at r equals 0. And I'm just curious, what was Einstein's view about this solution and its reality? Because we now consider it very relevant in many ways. In the course of his life, I thought the two of you might be able to comment intelligently about that question.
So I think about the singularity at the origin in the Schwarzschild solution. We tend to think about that nowadays as the result of a gravitational collapse. But of course, in the Schwarzschild solution itself, it's just a point particle source, just as you would use in electromagnetism, right? Where it's a point charge. So there was no view there in the original Schwarzschild solution that this singularity was anything else than an idealization of matter. And only later, with studies of gravitational collapse and the idea that this singularity somehow arose in a dynamical manner, did one even start to think about what it meant physically beyond being an idealization of a matter particle. So I think that's why it's not really an issue if you look at Schwarzschild or Einstein's reaction to that.
But of course, we know that the singularity, the coordinate singularity at the horizon in Schwarzschild coordinates bothered many people until Pascal and so on, which is 30-some years later. And Einstein, as far as I can tell, let's put it, never understood exactly. I mean, was confused over and over again by coordinate singularities. And this is most explicit in his 5 papers he wrote which proved that finite energy solitons don't exist in fluid-inclined theories, and they do. And he proved that they don't exist because what he meant by singularity-free solutions of his equations was a global patch, if you want. So you couldn't have monopoles or things like that. And so he proved that without that coordinate by singularity-free, he meant coordinate singularity-free, not real singularities. And he somehow never understood that. Which is what I used to explain to graduates, to the general audience, that today we understand general relativity better than Einstein.
And then evolution is one of the principal themes of the next day's discussion here. Before we get to the next question, I want to just ask here.
Yeah, just a brief comment, David. You asked at the beginning of your talk 2 historical questions, and I'll be very short in trying to answer them. The first was about the equality of inertial and gravitational mass, and whether Einstein was really the first to make this into a riddle or a challenge for physical explanations. He wasn't. The first one was Heinrich Hertz, probably. Heinrich Hertz, in his lecture notes on mechanics, emphasized that this was a strange coincidence. He didn't make much out of it, but he clearly perceived that there was something hidden there. The second remark is about the equivalence principle, whether the equivalence principle was generally accepted. Definitely it was not. All the competitive theories at the time, Hannah mentioned Abraham's theory, the most prominent one was Nordström's theory. They basically ignored the equivalence principle. So it was really a hallmark of Einstein's attempt to create a relativistic theory of gravitation.
But by ignoring it, did they ignore the unbelievably precise experimental evidence for the equivalence principle?
I mean, some of the contemporary theories of gravitation even talked about it, and they said, well, maybe you get some deviations from Galileo's principle that all bodies fall with the same acceleration, but those will be small, and the main thing is to create a relativistic field theory of gravitation, even if it violates that criteria. So Einstein was kind of stubborn in sticking to the principles of classical physics as well as to those of field theory. That between those poles he moved.
I have a question for the 2 speakers, but I'm sorry, it's again a question about symmetries. So I really appreciated this emphasis on symmetries because this is something that is coming out also in other talks. But I was wondering, historically, what was Einstein doing? Because it's true that he had this symmetry principle, but what he was doing, seems to me, he was taking seriously the symmetries that were known. So it was not about postulating some symmetries that were not observed in nature. It was about taking the symmetries that were already proved and trying to come back. I finished the question, then you can answer, of course. So yes, indeed, my question for you, David, is what are the principles, what are the symmetries, how do you choose the symmetries that are needed, that guide your new theory? So I know, I can tell you for the theory I work on, the loop quantum gravity, I can start by the Lorentz group, I can start from invariance by diffeomorphism, and these are the only symmetries that I assume from which I start. I don't have to add new things. This is the question for you, and the other question for Alex is related to how these symmetries should guide us towards the theory of quantum gravity, in the sense that, so when the old generation was talking about a unified theory, was it in the sense of this some new symmetry arising, or was rather trying to include the quantization? So to have a unique framework, I use your words, David, to have a unique framework to describe all the theories. So if we achieve, as maybe we have, a theory of quantum gravity, this is So we can describe gravity and matters using a unique object that is a framework in the sense that it's, for instance, a covariant quantum field theory. Then this is maybe the unification people had in mind in the old times.
I think Einstein, certainly special relativity and certainly in general relativity did not start with non-symmetries in space-time. He did know about Maxwell's equations, which he was sure were part of physical reality. He knew about, sure about Lorentz transformations, which Lorentz had derived from Maxwell's theory and Michaelson's Morley experiment. But Lorentz thought that those were properties of matter to be reduced from Maxwell's equations and not symmetries in space-time. In the case of general relativity, the general ordinary invariance principles of truth was totally invented. And indeed, Einstein, as I quoted, learned from this successful application of invention, speculation, theoretical speculation, a strategy which he applied for the rest of his life and which wasn't fashionable philosophically and was not, was sort of forbidden, which was to speculate. And much of the progress in fundamental physics over the last century has been just speculating, inventing new symmetries, new possibilities, and testing whether they can be consistent with observation. And so I don't see that Einstein, both especially in general relativity, were based on taking known symmetries. They were inventions, deductions, in the case of quantum electromagnetism, of new symmetries that people have not recognized at all. And Einstein encourages us to continue this exploration. Whether a quantum theory of gravity, which we can argue about where it's been achieved and to what degree unifies, gives us a unified theory of physics, is of course, as again, Einstein would have totally disagreed when I quoted it. Unless it describes matter that we observe and consist of, that's not a unified theory of physics.
Yeah, and my answer, I'm afraid, is going to be a bit disappointing. I think it's pretty clear that the view taken by those physicists in the post-Einstein time who thought about these things, about what a unified field theory should look like, were really not thinking about just a unified framework. For most people, it was clear that this framework was going to be some kind of quantum mechanical framework, but that was taken as a given. The goals that people like Pauli or Oppenheimer would set for such a unified field theory really consisted of these two elements. There was just going to be one kind of field, quantum field, which would include both forces and matter. There was hope that quantum field theory was on the right way because one could see how electrons radiated off photons and those transformed back into electron-positron pairs, which made the Maxwell equations non-linear because of the inclusion of matter. And so there was really a hope there that there would be such an idea, but it was just one quantum field. And then the second thing, which probably Pauli was the one to harp on even more than Einstein, was that this unified field theory would also have no free parameters. Most notably, the central free parameter that people focus on at the time was the electron charge, or the proton charge. And that was really like the grand hope of, at least until renormalization kind of made people do more calculation, less speculating, one might say. The great hope that would have this theory that would define the electron charge as well. So there's this idea that the unified framework itself might be called a unified theory, is something that comes up with two things turning out to be harder than they seemed, namely finding a unified field theory, even at a classical level, and finding a quantum theory of gravity. Both things, so both incorporating gravity into the established framework and of, at any level, unifying the fields we know in nature in a even halfway strong sense. Both of these things turn out to be so hard that one can nowadays legitimately also refer to, say, one theory of gravity as something that at least brings things into a unified framework, but that's certainly not something that people, say, in the 40s or so would have accepted as, I mean, Pauli would certainly not have said that counts as a unified field theory.
Okay, well, thank you very much. I will have to stop.